Hello and welcome to today's webinar about modeling and design of lattice tower structures. My name is Wieland Götzler and I will guide you through the webinar. My colleagues Gerlin Schubert and Andreas Hörold will help you with your questions. But before we start with the webinar, I will show you some options for a control panel. On the top of the control panel, you have a orange arrow to show and hide the control panel. There you can also switch to the sound check and sound configuration of your computer. And on the bottom of this panel, you can write down questions which my colleagues will try to answer you. If it's a more specific question, we will get in contact to you after the webinar. Now we can switch over to RFEM and start with the webinar with an empty position. We will define a new model, and today we want to have a webinar about lattice tower structures. We want to have a 3D model. Okay. At first, we want to start with tower structure model. We don't want to model the whole structure step by step with single members, because we want to have we want to know about the features and options of this model. In RF tower structure, you can define lattice tower structures for triangular plan structure or rectangular plan towers. You can define inner bracings, cross arms for electricity towers, as well as leg extensions if your tower is located on a mountain site, for example. And you can prepare tower supports. In our example, we want to have rigid supports, and then we can switch to the next mask, which is cross-sections. In this dialog, we want to define the cross-sections we want to use for our tower. So for now, we want to have a L100 section for one leg member, and in another part of our tower, we want to use L120 sections. For our diagonals on top of the tower, we want to use L70 cross sections. For other diagonals, we want to have L60 sections. As well as for the horizontals, we want to have L60 sections too. And for our horizontal bracing, we want to have L50 to 5 section and L60 to 6 cross section. To have a better overview about the cross sections, you can also type down comments over there. So for example, we want to use horizontal bracing, HB, horizontal members as an H, and we want to have diagonals. And for the leg members, L2 and L1. Okay, so now we can switch over to the next mask, which is tower segments. In tower segments, you define the overall height of the tower, the width of the tower. You will define tower segments and, in accordance to the segments, the cross sections. You can define, for example, constant width of the tower, like in our example, but you can also define a width change, for example, constant width in the top part and increasing width on the lower part. In our example, we want to have a tower of 17.1 meters. We want to have a top width of 1.65 meters. And on the right side, you can also see that there's an option widths via outer dimension or member access system. If you use outer dimension, the width of the length of the horizontal member over there will be shorter than which you have written over here, because if you use outer dimension, tower structure module will automatically remove the eccentricity from the corner of the cross section to the center of the cross section. In our example, we want to have clear measures, and that's why we want to use member axis system. So 1.65, and the width on the bottom, because we want to have a constant width of the tower, we want to have 1.652, and we will define different segments. We want to have a height of 1.1 meters on top. There you can see the division in the same time in the graphic. And we want to have 2 times 8 meters for the tower for the other segments. Now we want to define the cross sections of the tower. On the lower part we want to have the leg number 2. You can see the comment over there, L120 over there. I switched off the rendering mode to have a better overview also for the vertical bracings later. But as you can see in the graphic, the active segment is highlighted in red color. The next part is the L100 section, and also on top we want to have this cross section, L100. Okay. Now we can switch over to the vertical bracings, and in this mask you can define vertical bracings and divisions of them for the specific segments of the tower. We will start over there with the division, but we don't want to have a bracing in this part. We just created this division to have a horizontal member over there later. In the next part over there we will define some bracing, but at first we want to have also some division in this area. So I will divide this segment 2 in 1.62 meters, 0.88, 1.17, 4.33 is okay, and then 2 times 1 meter and 6 meter left. Now we can start from the bottom. We want to have diagonals, and how you can prepare it. You can click to the drop-down list where you will find some standard bracings like X diagonals, K left, K right, and so on. If you don't know how it looks, you can also access to the library directly with this button over there. And there you can see X diagonals, of course in X, diagonals upward, diagonals downward is the other direction. You can have K left, K bottom, and so on. If you don't find the bracing which you want to use for your structure, you can also define a new one where you can define lines and divisions, different cross sections, and so on. So it's completely up to you which bracing you want to use for this tower. So we will start at the bottom. Over there we want to have a K left, K diagonals left, and I want to use cross-section D2 for this. And we want to define 3 divisions. Now it looks like this. If you want to check it, you can also rotate it or zoom in and zoom out, so you can see that there's a K open to the left side. It's the same way like in RFEM. So when you press the mouse wheel, you can rotate and zoom by pressing additionally Control key of a keyboard. Okay, so we will go on now. Diagonal upward with the L60 section 2. Diagonal downward. This should be a K left 2 with just 2 divisions, and then again diagonal up, diagonal down, and again diagonal up, but with a bigger cross section because the height is quite bigger than the rest of the segments. Okay, L70. Now we can switch to the next mask, which is horizontal girths. And in the horizontal girths, you can see directly in the graphic, we have a highlighted dotted line over there. We want to have horizontal members on top of the tower and in a height of 7 meters. So over there, we want to use the horizontal beams, horizontal cross sections, which is H, L60, and on the top we have H2, so L60 sections over there. And now we can switch to the last mask, which is horizontal bracing. It's pretty much the same like vertical bracing. You have a drop-down list over there. And for example, I don't know which is number 4. I can also access to the library, and I can see over there, there are horizontals and cross bracing and so on. So there we want to have horizontal bracing in set node at 7 meters, and this should be the type number 3. So this one and the horizontal bracing cross sections can be applied over there. Okay, this was too fast. I will switch back to the module. You can see in the generate data dialog, there is an overview about member end releases and so on. You can also export this list, re-import it. You can switch member types and so on. So as you can see over there, there's a diagonal, for example, now this horizontal beam. We can take a look at the bracing. This bracing has member end releases at member start and member end, for example. And you can also check member rotations and so on. Okay. Good. So now, as you've seen, I've exported the tower to RFEM, and to do it manually, it would quite take a lot of time to define all the members step by step. Another advantage of tower structure is that it automatically defines also partial views. We will see in the design of the structure later that you can check utilization ratio easily if you use these visibilities. For example, you can switch off the rest of the structure and show only leg number 1 and 2, rotate it and so on. This is a good way to access some parts of the model and change some parts and so on. For now, we are finished with tower structure module, but we want to continue with tower equipment. In tower equipment module, the main task is to define, as the name already says, the equipment of the tower. You can define platforms, tubular extension, antennas, cable ducts, and so on. As you can see in the first mask, the tower structure is located automatically. You can check it. Leg member number 1 are the members 1 to 17. They are also highlighted on the structure in the background. And this is done automatically. We will continue with the next mask, which is platforms, and over there we want to define a platform, or we want to define 2 platforms on our tower. Tower equipment is basically comparable to tower structure because you have also libraries, for example platform libraries or antenna libraries, and by this button you can access the platform library, and there you will find a library of standard platforms made by Dlubal. You can define also your own library with the aid of RFEM by using parametric blocks, and you can use them in tower equipment module. For our tower model, we want to use inside platform, and there you will find the type PRA004, which we want to use. Over there you can see at the moment it's on the very bottom of the tower. So at first I will change the level. The small level set is from the bottom. The big coordinate set is in relation of the coordinate system origin. So at first we want to change the level set to 60 meters over there. And we want to change the alignment type to user-defined. This alignment type allows you to align the platform automatically to the tower, and a tower equipment module will determine the eccentricity from the cross-section of the platform member to the leg member automatically, and it will generate coupling members between of them. We don't want to have the coupling members, and that's why we want to use the user-defined alignment type. And over there I have to change some parameters of the platform. So beginning with the length and the width of the platform, we will start. We want to have 1.65 meters over there. These parameters over there, they are inside the block. You can also switch on the dimensions on the tower, but in our example I will skip this. We want to change the parameters step by step, 0.4, and the others I will change to 0.75. And now you can see that the platform is located automatically or correctly to the tower. We want to have the same platform again in another level, and I will just copy this and paste it to another line. We want to have this platform in a position of 13.5 meters. We want to use the user-defined too, but instead of changing all the parameters again, I just copy them from this list by pressing Control Copy, and I will paste them over there, and that's it. Okay. Now we can switch over to tubular extension, and we want to locate the tubular extension on top of the tower between the two platforms. So the upper height should be changed to 6.9 meters and the lower part to 3.6 meters. So we have an overall height of 10.5 meters. Over there we can also define offset in X and Y direction, or we can apply also a shielding factor. We want to apply a shielding because we have the tubular extension is shielded by the rest of the tower structure, and we can reduce the wind loads over there by this factor. Like for tower structure, we can change also the cross sections for the tubular extension. So I will change the segment to 0.5 meters. The rest of the tubular extension have the same cross-section, so I will just change the very top of this tubular extension to a hollow section according Eurocode, 60.3 to 4 millimeters. And the lower part is a 219 to 10. The next step is to define the antenna brackets. antenna brackets is pretty much the same as for platforms. There's a library with blocks inside tower equipment, and you can access it by the button over there. There you have standard antenna brackets like this one for 2D and also 3D antenna brackets over there. We want to locate an antenna bracket between the two platforms, and therefore we will use this type. We want to apply it at the object number 2 because it's the lower platform, so we will choose platform 2 nodes over there, and global position is a node number. This is the node number of the parametric block. So I will start with 17 over there, but I want to have it on another side, so I will increase this number and change the rotation to 0 degree. And as you can see, the upper node of this antenna bracket isn't correct right now. It isn't connected to the other platform, and therefore we will connect node number 2 with platform number 1, and there it's the same node, node number 20. Okay. Now we can go to the next mask, which is antenna groups. There you can define your operators for the antennas, or you can define standard ones. In our example, I will use Vodafone as an example operator. And now we can go forward to the next mask, which is antennas. Antennas is a bit different. It is a library of antennas, but it's not like platforms or antenna brackets. These are not parametric blocks inside our equipment. These are like a catalog of antennas, and there you can see dimensions of antennas, and also if you go to the extended information, you can see also load data for specific wind directions and also ice loads. There are quite a lot of antennas over there, but if you couldn't find the antenna you want to use, you can also create a new one. You can change the shape to one of the standard shapes. You can change the manufacturer and so on. It's completely up to you. And you can define, of course, you can define your own loading and use it in tower loading module later. In our example, we will use a Bosch antenna like this one. Okay. And we want to apply it to our antenna bracket. And there you can see it's also highlighted in red color. We want just to change the offset in Z direction to have it in the middle between the two platforms. And now we can go forward to the antenna spare areas. The antenna spare areas are areas at the tower where antennas could be located after the construction of the tower, but you want to follow this possibility of an antenna placement directly in your static calculation. So that's what we want to do in our example too. On top of the tower, we want to reserve some area to have an antenna later. So we can define width and height of the antenna spare area. And for the set level, I could write something down directly in the cell, or I can use the picking tool and click over there to a node of the tower structure. Next step is to define some weight. I use 1 kilonewton over there, and I have some ice load too, 0.5, and for example 0.6 for ice class G and ice class R. Okay, we can go on. The next is to define inner ducts, but we don't have an inner duct in our structure. This is for bigger tower structures. You could define like a tower. Inside the tower, you can define your own You can define something like like this structure, where you can change divisions for the vertical bracing. You can change the vertical bracing, define cross sections, tower supports, and so on. So this is like a simplified tower inside your tower. Okay, we don't want to use this option in our tower because it's really small, and we don't want to have it in a duct. So I will remove it and switch over to cable ducts. In that cable duct mask, you can define cable ducts with a rectangular, circular, or row shape. In our example, we want to have a rectangular cable duct at leg number 2. We want to have it from set level 0 to the very top of the tower, over there, with the width of 0.1 meter and a depth of 0.1 meter. You can see it in the graphic. What is left is to define a weight, which is about 0.5 kilonewton per meters. And of course, we have to connect this cable duct to our tower somehow. And therefore, we can use connect to member or connect to nodes. In our example, there we have location at leg number 2. We want to use member nodes, connect to nodes. And as I told you, tower structure automatically generates visibilities, and there you can just create an area all above leg number 2, and you can select all the nodes of leg number 2 to connect the cable duct to the tower. Okay, the last step is to define a ladder, and there we want to have a standard shape ladder in location of leg number 1 with no rotation. And we want to connect the ladder to leg number 1 nodes over there. I didn't use these 2 nodes because the ladder starts at the 3rd node over there. Okay, the last step is to export the equipment to RFEM, and then we can go forward to prepare some loading to the tower. Okay, saving the position, saving the model. Okay, now we can switch off maybe the dimensions, and we can go forward to tower loading module. In tower loading, you can see, like in tower equipment, the structure is located automatically, and we can skip this mask to dead load. In the dead load, it's on the top, it's like an overview about the self-weight loads. You can also define factors if you have some sheeting, or you want to apply some additional self-weight to the legs, for example. You can also define additional surface loads on platforms if you have some sheeting on these. But in our example, we don't want to use this. We want to skip directly to wind load part number 1. In this mask, you can define wind loads according to several standards. You can use Eurocode settings as well as DIN settings. Because the DIN settings for wind loads according Eurocode are a bit different, that's why we have also written there according Eurocode and /DIN settings. But if you want to apply wind loads according Eurocode, you can use this wind pressure for several standards, and it will generate the wind loads automatically to your tower. In our example, we want to use French annex, for example, to apply loads according Eurocode. By clicking on this information button, you can skip to the mask, to a map. And for example, I will use Lyon for wind load location. If you want to use your own wind pressure, you can also define this manually in the table on the bottom of this mask. And on the right side you can define uniform steps to apply wind loads, but 15-degree steps will generate a lot of load cases, and of course we want to keep it simple. In our webinar I will change it to manually defined directions, and we want to inspect 0-degree wind load direction and 45-degree. Okay. Next is wind load part number 2. In the part 2 you can define effective slenderness of the tower to reduce the wind load, and you can define the type of cross-section for the calculation of force coefficients according to Eurocode. We have edge profiles, and we can keep these standard settings over there and skip to the next mask, which is structural factor CSCD according to Eurocode. There you can define, you can leave it as it is. You can define according to Eurocode in automatic calculation. You can also switch to complete manually structural factor CSCD, or you can set just the first natural eigenfrequency. If you use manually completely, you just have to define the structural factor. If you want to use first eigenfrequency manually, you can define additional parameters and the structure damping coefficient. We want to use automatic way and can skip to the next mask. This is shielding. Shielding is like an overview of our shielding factors made in tower equipment. There we have a tubular extension shielding factor in the lower part of 0.8 for both wind directions, which is okay, and for the ladder and the cable duct we don't want to reduce the wind loads. Now we can go on to the icing masks 1.7 and 1.8. In the mask 1.7 you can define the ice loads according to two standards, German DIN standard or more international ISO 12494 standard. We will switch to ISO, and we want to use ice class G2, and we want to use the antenna ice loads from database. Over there you could also change to calculated or user-defined settings if you want to have a user-defined ice load at this antenna. It's the same for ice class R. We want to switch to R2 for this example. And now we can move forward to variable loads. In the variable loads mask you can define uniform surface loads on platforms, single loads on platforms, and you can define also maintenance loads on all members with a slope smaller than 30 degrees. But in our example we don't want to use the variable loads, and we will switch them off completely because we only want to inspect wind loads and ice loads. The last step is to generate the loads. You can see 3 calculations over there. And why there are 3 calculations? Because we have to calculate the first eigenfrequencies of the structure, and this is made by RFEM module to get the natural eigenfrequencies of the tower, and with these frequencies we can calculate the structural factor CSCD to increase the wind loads. In the result tables you can check all the results step by step. You could recalculate all the wind loads step by step. If you want, for example, I want to check the wind loads for wind direction 0 degree and on the left side. 0 degree means parallel to x-axis. So we are in this area over there, which is highlighted in red color, and there we can check all the calculation inside the bottom of the table. Okay, now we can export the wind loads to RFEM, and we can leave the module. We can skip to show the loads, for example self-weight, for example ice, and wind loads. Now we want to combine the loads. Therefore, I will switch on the automatic combination of load cases in the general data of the structure. First, I will switch to the French annex and create all combinations automatically. We want to define load combinations automatically. Okay. And we can switch to added load cases and combinations. In added load cases and combinations, we have to select action categories for our load cases, for example, ice and wind in our example. Okay. Next is to check the actions. That means we have only self-weight. In permanent loads, we have alternatively acting ice weight, and we have alternatively acting wind loads. Now we want to check combination expressions. We can remove the serviceability limit state in our example, and we want to check only the ultimate limit state. What we want to do now is we want to remove the amount of load cases, and therefore we will switch to individually simultaneously acting load cases. In this mask, we can define that ice load class G should only be combined together with wind ice load G. That means we want to order the load cases together somehow. That means wind 0 degree should not be combined with ice weight, because therefore we want to use the LC5 wind 0 degree ice G. Okay, so we will select ice weight class G. Should be combined only together with wind ice G, and that's it. And the same for ice class R. And we have to do it vice versa. I will copy the load cases over there to reduce the amount of combinations. That's it. We can skip to action combinations. And then to load combinations. Over there you will see that we have 11 load combinations, and you can take a look at them separately. For example, load combination number 2 is self-weight ice class G and wind ice weight class G. And of course, wind separately with self-weight and so on. Okay, that's it. We can move on to prepare the design of the structure. Before the design, we could also use tower effective lengths to generate effective lengths of bracing members, but in our case we have just diagonals and no X bracing, for example, and we don't need to calculate effective length factors automatically. We can skip directly to tower design module, and there we want to design the structure according Eurocode 3 with French National Annex. We want to design all the members and all the load combinations. We want to disable small bending moments for stability check, and therefore we will switch to stability design, and we can type down ratio of bending moments to disable these bending moments from stability check. That means if you have a bending moment MYED to M plastic YERD of about 15%, the program will run only stability check for normal forces and not for interaction of normal forces and bending moments. Okay. We can check member types, and these are again all located automatically. Materials, we have S325 and S355 for antenna brackets and platform members, cross-sections, and effective lengths of the tower, bracing members, and now we can run the calculation. And we have a design of about 68%. And can take a look at the cross-sections. For example, design by cross-sections. We can switch on maximum design, for example, and check the stability analysis of the L70 section. You can check the calculations step by step in the bottom table over there, cross-section classification, design ratio, and so on. You can check all these calculation parameters step by step. And the last step would be to define printout report, but in order to keep it simple, and we are finished with calculation now, we are pretty much at the end of our webinar. I will just save the model right now and skip to the presentation. Now we have to go from the last slide. Okay, so for more information, please check our website, dlubal.com. You can follow us on Facebook, Google+, Twitter, and other social media. If you have any questions, please write an email at info@dlubal.com, or you can also phone us to get additional information. Our next webinar is at the 26th of March in 2015. And there we want to check natural eigenfrequencies and equivalent static forces analysis with RFEM. I want to thank you for your attention and looking forward to our questions and interest. Thank you very much.